we want to talk about ways to determine whether or not a polynomial is separable. And so what are we asking? We're asking whether or not a polynomial has a multiple root in a splitting field. And the way that we're going to understand that question is by looking at the derivative of the polynomial. Okay, so let's say our polynomial f of x is an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a0. This is in f bracket x. Its derivative is defined to be the polynomial that we would get by just applying the power rule to every term and adding. So dx of f of x is defined to be n times an times x to the n minus 1 plus n minus 1 times an minus 1 times x to the n minus 2 plus 1 times a1 times x to the 1 minus 1, which is 0, plus 0. So this polynomial in f bracket x. Okay, so why are we defining a derivative at all? Well, we have this usual notion of a derivative that you learn in calculus, and it has to do with limits, with these continuous things. We're taking the limit of, as h goes to 0, of f of x plus h minus f of x over h. And we just don't know how to do that in a general field. For example, if f is a finite field, what does it mean to take the limit as h goes to 0 of something? So here, this idea is that this definition is purely algebraic. So it starts from the idea that what should the derivative of a polynomial look like? It starts from the power rule, that if you have the derivative of one term, you should get it by applying the power rule, and then you should get the derivative of a polynomial just by adding up the derivatives, so that the derivative of f plus g should be the derivative of f plus the derivative of g. Okay, so we're only going to apply this notion of derivative to polynomials. So we also have a much simpler task. We don't have to define the derivative of like any differentiable function. That's not something we're going to talk about. So this definition is purely algebraic, and it's easy to remember because it just comes from the power rule, and you can apply it over any field f. So it's an exercise in section 13.5. It's exercise 1 to show that this definition of derivative maintains some of the nice properties that you're used to from derivatives in calculus class. So the derivative of f plus g is the derivative of f plus the derivative of g. And the product rule holds. The derivative of f times g is the derivative of f times the derivative of f times g plus f times the derivative of g. And this is true for any polynomials f and g in f bracket x. All right, so what do derivatives tell us at all about polynomials being separable? Well, we get a way to tell whether a polynomial has a multiple root by saying something about the derivative. We're going to prove that f of x has alpha as a multiple root, if and only if alpha is a root of f of x, and alpha is also a root of the derivative of f of x. So in particular, when does f of x have no multiple roots at all? That is when f of x is separable. F of x is separable if and only if the GCD of f of x and the derivative of f of x is 1, that they have no common factor of positive degree. If they had a common factor of positive degree, any root of that common factor would be a multiple root. Okay, so let's prove this. And I'll start with the direction where we suppose that alpha is a multiple root of f. And we're going to show that alpha is a root. I mean, if alpha is a multiple root, it's certainly a root of f. So all we have to do is show that alpha is also a root of the derivative. Okay, so let's take a splitting field for f of x over f. And let's factor f of x in this splitting field. So we get x minus alpha to some power. We know it's at least 2 because it's a multiple root. So the multiplicity of this root is at least 2. So we can write f of x as x minus alpha to the n times g of x. We could also pull out all of the factors of x minus alpha from g of x so that we could write it this way, where g of alpha is not equal to 0. But we don't even have to do that. All we have to note is that we can write f of x as x minus alpha to the n times g of x, where n is at least 2. And now we're going to apply this product rule and say, okay, well, what is the derivative of f of x? It is the derivative of x minus alpha to the n times g of x plus x minus alpha to the n times the derivative of g of x. And now we just need also to note that the derivative of x minus alpha to the n is n times x minus alpha to the n minus 1, which you can prove. I guess this isn't like super direct from the definition, but you can prove this using the product rule. So I'll leave that for you to think about. Okay, so now we know the derivative of f of x can be written this way. And we just have to plug in alpha and see what we get. You put in alpha, x minus alpha to the n minus 1 when x equals alpha is 0 to the n minus 1. Since n is at least 2, that's 0. And here we have alpha minus alpha to the n, which is also 0. So as long as n is at least 2, this is 0 plus 0. So alpha is a root of the derivative as well. Okay, so I'm going to pause and erase, and we'll prove the converse direction, that if alpha is a root of f of x and a root of the derivative, that alpha is a multiple root of f. Let's finish the proof of this proposition 33. We've already proven that if f of x has alpha as a multiple root, then alpha is a root of f of x and is a root of the derivative of f of x. So now let's suppose that alpha is a root of both f of x and its derivative. And let's show that f of x has alpha as a multiple root. So let's keep this notation that L is going to be a splitting field for f of x over f. We know that alpha is a root of f, so we can write f of x as x minus alpha times some polynomial h of x in L bracket x. So let's use the product rule to write down the derivative of f of x. So it's the derivative of x minus alpha, which is 1 times h of x plus x minus alpha times the derivative of h of x. And what do we know? We know alpha is a root of this polynomial as well. So since alpha is a root, when we plug it in, we get h of alpha plus alpha minus alpha times this derivative evaluated at alpha. Doesn't matter what that is because alpha minus alpha is 0. So what we get is that h of alpha equals 0. And this is good because what does that mean? That means that h of x, some polynomial in L bracket x, has x minus alpha as a linear factor. But that means that f of x has x minus alpha squared as a factor. So it's x minus alpha squared times h1 of x in L bracket x. Now we're done. Now we've seen that alpha is a multiple root of f of x. So what have we proven? We've proven that f of x has alpha as a multiple root if and only if alpha is a root of both f of x and the derivative of f of x. And so we want to say that f of x has no multiple roots if and only if the GCD of these two polynomials is 1. So let's just say clearly, like, what does it mean for alpha to be a root of both of these polynomials, f of x and the derivative of f of x? Well, when is alpha a root of a polynomial? When the minimal polynomial of alpha divides that polynomial. So if alpha is a root of f of x, then the minimal polynomial of alpha divides f of x. And if alpha is a root of the derivative of f of x, the minimal polynomial divides this derivative. So the minimal polynomial divides both of these if and only if, so if alpha is a root of both of these, then the minimal polynomial divides both of these. So the minimal polynomial divides the GCD of both of these. Okay, so we've seen that the only way for f of x to have no multiple roots is if this GCD has no factors of positive degree. All right, so where are we? If you want to know whether or not a polynomial is separable, you can check what is its GCD with its derivative. Is it 1 or is it not 1? And how do you compute the GCD of two polynomials? Using the Euclidean algorithm in f bracket x. So what we've seen is that we now have a way to start with any polynomial and determine whether or not it is separable. We just do the Euclidean algorithm with the polynomial f of x and its derivative. So I just want to give an example here just to show you what this is like, because this can be now kind of like a mindless process. We've been talking about the Euclidean algorithm in f bracket x for a very long time now. We've seen that it's useful for lots of things. So here's an example. Let's take f of x to be x to the 6th plus x to the 5th plus x to the 4th plus 2x cubed plus 2x squared plus x plus 2 in f3 bracket x. This is an example taken from Conrad's notes on separability that I highly recommend that you check out. This polynomial is inseparable. Okay, so that could be an exercise for you to do, like on a homework or an exam or something. One thing you could do is factor this polynomial in a splitting field and see that it's inseparable. But it's easier not to do that. Like, it's easier to take the derivative by applying this power rule, like simple process to get the derivative, and then applying the Euclidean algorithm. So what is the derivative? Well, you get 6x to the 5th plus 5x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1. But in f3 bracket x, this 6 is 0, this 6 is 0. So we get 2x to the 4th, because 5 is the same as 2, plus x cubed plus x plus 1. And now it's not so hard to see that this factors. And there are not so many possibilities in f3 bracket x. This factors as 2x squared plus 2 times x squared plus 2x plus 1. Okay, so now how do you actually apply the Euclidean algorithm? Well, you do the division algorithm. You divide the derivative into f of x, and you see that f of x is equal to the derivative times 2x squared plus x plus 2x plus 2. But now you see that 2x plus 2, we know it divides the derivative. So it divides both terms in this sum. So it also divides f of x. So you can check that the derivative actually is 2x squared plus 2 or x squared plus 1, since 2 is a unit. These are the same. But at this point, you can already see that the GCD of f of x and its derivative is not 1. So in a splitting field, f of x does have a multiple root. You can check that this is true. You can see that if you factor f of x over f bracket x, then you get x squared plus 1 squared times x squared plus x plus 2. But what I'm trying to emphasize here is that we can see that f of x is not separable at this point. We can do that without actually factoring f of x, which can be sometimes like a little bit challenging to do. So you can check whether or not a polynomial is separable using the Euclidean algorithm, which is less work than factoring it in f bracket x. So I'll pause and erase and talk about a couple more examples. Let's continue our discussion of examples. Let's take the polynomial x to the p to the n minus x in fp bracket x. This polynomial is separable. Like I said at the very beginning of this lecture, most of the interesting stuff that's going to happen with separable polynomials and inseparable polynomials is going to happen in characteristic p. So here's an example. What's the derivative of this polynomial? Well, it's p to the n times x to the p to the n minus 1 minus 1. But in fp bracket x, p is 0, so p to the n is 0. This just is the polynomial -1. Okay, so alpha is a multiple root of f of x if it's a root of f and its derivative. But this derivative is the constant function -1. It doesn't have any roots. So another way to say that, I mean, that what I'm saying now is stronger than just pointing out that the GCD of f of x and its derivative is definitely 1. There are no multiple roots. This is a separable polynomial. So we'll come back to this polynomial and really look at it carefully in the next lecture. Let's think about x to the n minus a, where a is some non-zero element of f. This is a polynomial in f bracket x. What's the derivative? Well, it's n times x to the n minus 1 minus 0. So this is n times x to the n minus 1 in f bracket x. Okay, well, 0 is not a root of f of x. You plug in 0, you get minus a, which is not 0. So what do the roots of the derivative look like? Well, the only root of this polynomial is 0 unless the whole polynomial is 0. Right? So if n is at least 2, then 0 is a root. And it's the only root, clearly, unless the whole polynomial is 0. But when does that happen? That's if n is 0 in f. That is, if the characteristic of the field divides this integer n. Okay, so what does this tell us? Well, x to the n minus 1 is separable if the characteristic of f does not divide n, because then f of x and its derivative have no roots in common. So what does that mean? That means that x to the n minus 1 has n distinct roots in a splitting field of x to the n minus 1 over f. Okay, so in particular, if the characteristic of f is 0, the characteristic of f is 0, so n times x to the n minus 1 does not divide, the characteristic of f, 0, does not divide n. So n times x to the n minus 1 is not the 0 polynomial. In characteristic 0, there are no common roots between f of x and its derivative. So x to the n minus 1 has n distinct roots. What's the field of characteristic 0 where we've talked about this before is q. X to the n minus 1 in q bracket x is separable. That means that in a splitting field for this polynomial over q, we have n distinct roots of this polynomial. And this goes back to a few lectures ago when we talked about the cyclotomic field, the nth cyclotomic field, or the cyclotomic field of nth roots of unity, which was a splitting field for x to the n minus 1 over q. So there was one splitting field where we could describe it explicitly in terms of e to the 2 pi I over n and powers of it, these like complex nth roots of unity. But in an abstract splitting field, it was not clear that there were n distinct roots of this polynomial in a splitting field. So Dummett and Foote say we'll come back to this later, and this is when they're coming back to it. So you could already know this, that there are n distinct roots in a splitting field, because any splitting field has to be isomorphic to the one splitting field that we described as a subfield of the complex numbers. But this is really explaining like why there are n distinct roots of this polynomial in any splitting field for this polynomial over q, because this polynomial is separable over q. Okay, so let's talk about the case where the characteristic of f does divide n. So in that case, x to the n minus 1 is inseparable. So this is for n at least 2, because, well, the derivative is 0. And that means, what does it mean for alpha to be a multiple root of f of x? It means it's a root of f of x and it's a root of the derivative. If the derivative is 0, alpha is automatically a root of the derivative. Every root alpha of x to the n minus 1 is a multiple root of x to the n minus 1, because the derivative is 0. You get that alpha is a root of the derivative for free. Okay, so I'm going to pause and erase, and I'll talk about some additional facts that you can see about separable and inseparable polynomials by thinking about how a polynomial f of x factors in a splitting field. I want to mention 2 more results that you can think about. And the idea is that if you have a polynomial f of x and f bracket x, you know what it means to be separable is that it has distinct roots in a splitting field for f of x over f. So one idea is, if you think about how a polynomial factors over a splitting field, that should suggest how to prove the following 2 statements. So these both come from notes by Keith Conrad called separability. I definitely encourage you to check out these notes. And the first one says, okay, so if f of x, a polynomial in f bracket x, is separable, and L is an extension of f, then any factor of f of x in L bracket x is separable. So you have f of x that factors some way in f bracket x. You can go to this larger field, L bracket x. So maybe those factors that might be irreducible in f bracket x no longer are reducible in L bracket x. But if f of x has distinct roots in an algebraic closure, then you factor in L bracket x, you pick out some factors, and each one of those factors has distinct roots in an algebraic closure. Sorry, in a splitting field, not algebraic closure. Has distinct roots in a splitting field also. Okay, so along with this, now if you have fields f contained in k, so k is an extension of f, and L is an extension of k, L is an extension of f. So fields f contained in k, contained in L. And if L is a separable extension of f, so every L is algebraic over f, and every alpha in L is separable over f, meaning the minimal polynomial of alpha over f is always a separable polynomial, then, okay, every alpha in L is separable over k. So what we're saying is alpha is algebraic over f. It's also algebraic over k. So what is this saying? This is saying that the minimal polynomial of alpha over k is a separable polynomial. So to prove this statement, all you have to think about is how are the minimal polynomial of alpha over f and the minimal polynomial of alpha over k related to each other. So I'll leave the details to you. You can also go to these notes and look up a full proof, but it'll probably be better if you try to prove this for yourself first. Okay, one more result that I want to mention. If you have an injective homomorphism from a field f to a field k, so what does that mean? That means that the image of f is isomorphic to a subfield of k, so k has a subfield isomorphic to f. You have this injective homomorphism of fields, then if you have a polynomial f of x in f bracket x, it is separable if and only if the polynomial sigma of f of x, which is in k bracket x, is a separable polynomial. Okay, so think about what does it mean for a polynomial to be separable? It means that the GCD of f of x and its derivative is 1. Okay, well, if you want to say something about the GCD of sigma of f and the derivative of sigma of f, then you need to know something about the derivative of sigma of f. So along the way, you might want to prove for yourself that if you apply sigma to this, okay, so being a little loose here, right? We have this homomorphism from between these two fields. This extends to a homomorphism from f bracket x to k bracket x that you get by applying sigma to the coefficients of your polynomial. So, okay, so now it's clearer what this means. This is you apply sigma to the coefficients of f. You'll want to check for yourself that if you take the derivative and apply sigma to the coefficients, what you get is the derivative of the polynomial that you get by applying sigma to the coefficients. So I'll leave that for you to work out the details. Again, you can go and look up a full proof in Conrad's notes if you would like, but I recommend that you work this out for yourself first. So where are we? We know that if you have a polynomial, you can check that it's separable by checking whether or not the GCD of f and its derivative is 1. In the case that your polynomial is irreducible, thinking about how f of x and its derivative are related, we'll see that we have a much easier way to check whether or not an irreducible polynomial is separable, and that will be the topic of the next video.